In any case, the first part, the first 2 minutes has been recorded. In this figure, I'm considering the problem of placing particles into energy states. So for simplicity, the particle has just 3 particles. The energy states are quantized and they are equally spaced. So the lowest is 0. Then we have one energy state at Z, energy equal to Z, then 2Z, 3Z, and so on. And we assume that these 3 particles are in an equilibrium condition in which the total energy is 3 times Z. Okay? And we must consider all the possible ways to place the particles into the available energy states in order to fulfill the constraint on energy, that the total energy must be 3 times Z. Obviously, we must consider the case in which the particles can be placed all together in the same energy state Z. This is the situation that you can see in the first column on the left. All particles are placed at energy Z. So of course the total energy of the 3 particles is 3 times Z. A second possibility is to place one particle at 0, so no energy. Another particle at energy equal to Z, and finally the third particle at some energy equal to 2Z. Okay, so you see this in the second column from the left. 0 plus Z plus 2Z again makes 3Z, so the total energy is preserved. But at this point, we must distinguish between 2 possibilities. And these possibilities are, number 1, the particles are identical from the mechanical viewpoint. So they have the same size, the same mass, everything is equal, okay? But at the same time, the particle can be distinguished from each other. So it is like you have a billiard. In the billiard, all balls are equal. They have the same mass, same diameter, same smoothness of the surface. Everything is the same. But they have a different color. So you can distinguish the balls in a billiard thanks to the color. In this case, we have 3 particles. We assume that they can be distinguished from each other. So we have the white one, the gray one, and the black one. Okay. So you see immediately that there are 6 possible combinations of placements such that you have one particle at 0 energy, another particle at one level, and the other particle on the second level. You see that if you look at columns 2 and 3 from the left, you see that you can place the white ball on top, and then you have two possibilities for the black and the gray. Or you may place the gray ball or the gray particle on top, okay, and you have other two possibilities. And finally, you have placed the two black particles on top. So you have a total of 6 possibilities of placing the 3 particles such that one particle is at 0 level, one is level 1, and the other is at level 2. Finally, there is another possibility to achieve the total energy equal to 3. One particle goes at level equal to 3Z, and the other 2 particles go to level 0. And again, if the particles are distinguishable, you may decide to place the white particle on top, or the gray particle on top, or the black particle on top. So you have a total of 3 combinations. Conclusion: the total possible placements of 3 particles into the energy states fulfilling the constraint of having a total energy equal to 3, and assuming that the particles are distinguishable from each other, are the 10, total of 10 combinations shown in the figure, okay? 1 of the first type, 6 of the second type, and 3 of the third type, okay? So if you consider that the particles continuously interact with each other, they change the configuration from one to another continuously, okay? So they are not fixed in any of these configurations. They change in time, okay? So if you take a picture every second of the system of 3 particles, you will find one of the pictures shown in the figure, okay? However, you notice that the combinations in the middle, those that are 6, okay, their number is larger. So it is reasonable to understand that if you take pictures, a larger fraction of the picture will show the system in the positions 1, 2, and 3, or sorry, 0, 1, and 2. Okay, simply because there are 6 possibilities. Instead, there is only one possibility for the 1, 1, 1 case, and 3 possibilities for the 3, 0, 0 case. Okay, so we define the combination that occurs more times as the equilibrium condition. So the equilibrium condition for this example is 0, 1, and 2. This is what happens in the classical case. The classical case is the case in which the particles of the system can be distinguished from each other. However, it happens that microscopic particles are not distinguishable. All electrons are equal to each other. There is no way to color the electrons in a system, okay? So all electrons are equal. Also, other microscopic particles are equal to each other. for instance, photons of the same frequency are equal to each other, they cannot be distinguished. Okay? So, if you consider the case of photons, for instance, you must say that the first column is still possible, like in classical mechanics, okay? But the 6 columns that go from 2 to 7 in this figure, those that have one particle at 0, one at 1, and one at 2, they cannot be distinguished. There is no white photon, gray photon, or black photon, okay? So the 6 original combinations actually are just one possible combination, okay? And the same applies for the last 3 combinations. So if they are photons, these 3 combinations are just one, okay? So for particles like photons, only 3 cases are possible. One case is 1, 1, 1, the first column on the left. The second case is the group of 6 that reduces to one case, 0, 1, and 2. And the third one is that made of the last 3 columns, one particle at energy equal to 3 and 2 particles at energy equal to 0, okay? Photons belong to a larger class of particles that are called bosons, okay? So you can see at the bottom of the figure, C equal to 1, 6, or 3 describes the combinations of the particles in the classical case. So C stands for classical. In the second line, B equal to 1, B equal to 1, B equal to 1 describes the case of the quantum particles of the family of bosons. So B stands for bosons. And then we have another possibility, still for microscopic particles that follow the rules of quantum mechanics. And this is the family of particles that are called fermions. Fermions are particles that, first of all, are indistinguishable, okay? But they have one more property, and this property is that they don't like to stay together. So it is forbidden to place fermions in the same state. State indicates energy and spin, okay? So two fermions in a system of fermions cannot have the same energy and spin at the same time. It follows that the left column is forbidden for fermions because you cannot place more than one particle in the same state. But also the last 3 columns are forbidden for fermions because they have 2 particles in the same state. Okay? So the impossibility of placing 2 fermions or more than 2 fermions in the same state goes under the name of exclusion principle, or also Pauli principle, okay? The Pauli principle applies only to the family of fermions, does not apply to the family of bosons, okay? So when we consider fermions, and electrons are fermions, essentially only the mid part of the combinations is allowed, that is one particle in the state equal to 0, the other state equal to 1, and the other state equal to 2. And all these combinations reduce to just 1, because fermions also are indistinguishable from each other. Conclusion: this very, very simple example shows that the placement of the particles in the available energy state depends also on the nature of the particles. Because besides fulfilling the constraint on the total energy, you must fulfill the constraint for quantum particles, also on the indistinguishability of them, and in the case of fermions, an additional constraint due to the exclusion principle. So the placements turn out to be very, very different. Okay? When we have a system made not of 3 particles, that is the easy example, but of a large number of particles, and this system is made of electrons, we find the equilibrium statistics exactly in the same way. We just place the electrons in the available energy state. And for a crystal, the available energy state are those prescribed by the band structures, the band structure of the crystal. Okay. The calculation is not so easy because when you have a large number of particles, I mean, the combinations become immediately very, very many. Okay. But the calculation can be done smoothly and provides a result. And the result is the so-called statistical distribution of the electrons in a system at equilibrium. Okay? This statistical distribution provides the probability that in a system of electrons, one electron has an energy equal to some value. Okay? We shall see the expression immediately. I just changed the page here and go. No, sorry, I am the wrong page. Sorry. Okay. Okay, the expression of interest is this one. Okay, so the calculation following the placement of the electrons in the available energy state, fulfilling the constraint that the total number is conserved, that the electrons are indistinguishable from each other, and that they fulfill the Pauli principle, provides a statistical distribution that has the expression shown here. So P of E is the probability that one electron in the system has energy equal to E. This is the meaning of this formula. Since the electrons are very many, in doing this calculation, at some point, we forget that the energy levels are discrete, okay? Because there are so many that we consider them as continuous, okay? But remember, the energy levels are discrete. You see immediately that the denominator is larger than 1 because it is 1 plus an exponential. So this function is always positive and is always smaller than 1. In conclusion, we can consider it properly as a probability, okay? It takes the name of Fermi-Dirac statistics because it was found independently by Fermi and Dirac. In the expression, there are parameters. One parameter is Kb. Kb is the Boltzmann constant, so it is a universal parameter, okay? Never changes. The other two parameters are the absolute temperature. Of course, since we are considering a system at equilibrium, the absolute temperature is well defined. The temperature of the system is well defined, okay? So T is the absolute temperature calculated in Kelvin. E sub F is another parameter that is called the Fermi energy or Fermi level. It depends on temperature. It has a weak dependence on temperature, okay? But in many cases, we shall neglect this dependence on temperature. Obviously, E and E sub F are energies, so they are measured in joule, which means that KT is also measured in joule. So Kb, the Boltzmann constant, is measured in joule over Kelvin, so that the product Kbt is joule. The numerical value of Kb is 1.38 times 10 to the minus 23rd joule over Kelvin, okay? We can consider some limiting cases of the Fermi statistics. For instance, if the exponent of the exponential is large, then the exponential is also large, and we can neglect the 1. So an approximate form of the Fermi statistics is this one. It's in the last line. When you neglect the 1, you have exponential of EF minus E over KT. You extract the exponential of EF over KT, call it P0, times exponential of minus E over KT. So this is the typical distribution that you apply to the classical particles, and it goes under the name of Maxwell-Boltzmann distribution, okay? It is not a probability anymore because it is not limited between, it is positive, but it's not limited between 1 and 0. And if you take larger and larger values of energy, you see that the Fermi statistics and also the Maxwell-Boltzmann statistics, they go to 0. So for very large energy, they vanish. This is physically obvious. Since the total energy of a system at equilibrium is given, it is impossible for the particle to have an energy that is arbitrarily large. Okay, so the probability of arbitrarily large energy must be vanishing, okay, because of that. We may also have the opposite situation. You may consider values of energy that are smaller than the Fermi level. So the exponent becomes negative. And if this exponent becomes very negative, the exponential becomes very small. So in this case, the unity at the denominator dominates, and the limit of the Fermi statistics to the left is equal to 1. Okay? The final observation is that for the value of energy E that is exactly equal to the Fermi energy, the exponential becomes equal to 1, so that at the Fermi level, the Fermi statistics becomes equal to 1/2. Okay? And we should also see the graph here. Okay? So in this figure, the abscissa has been taken equal to E minus the Fermi level. So when E is equal to the Fermi level, then as you see, the curves cross the point 1/2. For very large value of energy, so when we go to the right in the diagram, the limiting value is 0. And when we go to the left, so for values of energy that are smaller than the Fermi level, the limiting value is equal to 1, which means that energy states whose energy is smaller or significantly smaller than the Fermi level, they have a probability of being occupied by one of the electrons of the system, which is practically equal to 1. So they are all occupied. What does distinguish the curves of this figure from one another? The temperature. So these figures have been drawn using temperature as parameter. Okay, so they have been drawn by changing T here. And the black squares are related to the high temperature situations. The gray and not so gray and white squares are with low temperature. So you can see that at large temperatures, the Fermi statistics increases beyond the Fermi level and decreases to the left of the Fermi level. This is somehow reasonable, because if you have a system of particles and you increase the temperature with respect to the original temperature, in order to do so, you are giving energy to the system from the outside, okay, from the environment. If you give energy to a system of electrons, some of these electrons will become more energetic. So they will occupy energies that are larger than the Fermi level. So there will be a larger fraction of the electrons in energy states larger than the Fermi level. On the other hand, the total number of electrons is given So if you have more electrons on the right, you must have less electrons on the left. So the probability to find occupied states on the left will decrease. The opposite occurs when you decrease the temperature of the system, because you are subtracting energy to the electrons, so they will become less energetic. So it will be more and more difficult for the electrons to occupy high energy states, and a larger probability for them to occupy low energy states. So if you look at the curve corresponding to the white square, okay, and consider decreasing the temperature even more, okay? So the curve will deform and will eventually become identically equal to 1 to the left of the Fermi level, and it will become identically equal to 0 on the right. So in the limit of temperature going to the absolute zero, T going to 0, the Fermi statistics becomes a box. It is a discontinuous function that is equal to 1 for energy smaller than the Fermi level, equal to 0 for energy larger than the Fermi level, and it will still be equal to 1/2 at the Fermi level. Another important consideration is this. You see that the horizontal scale is normalized, okay? But one may ask the question, how much energy is necessary, or how much change in energy is necessary to go from almost equal 1 to almost equal 0, okay? So the transition from 1 to 0, okay, occurs in some energy interval, and it is of interest to understand whether this energy interval is large or not so large, okay? We make an intermediate step, okay? If you look at the curves of this figure, you see immediately that their slope is almost 0 to the left. Also, the slope is almost 0 to the right, and the slope is large and negative in the middle. So if you take the derivative of this curve and you change the sign, so the negative slope becomes positive, you obtain a set of curves like this. Okay, this is just minus the derivative of the Fermi statistics at different temperatures. Okay, and you see that when you increase the temperature, that means you consider the black square, the peak becomes wider. If you decrease the temperature, the peak becomes narrower, okay? And we are now interested in understanding how large is the peak at some given temperature, because the width of the peak gives you an indication of how much it takes for the function to go from nearly 0 to nearly 1, okay? It's an easy calculation. If you want to calculate how much energy is necessary to go from E equal to 0.9, okay? Not 1. Reaching 1 is impossible because you should go to minus infinity. From 0.9 to 0.1, okay, it takes about 4 times kT. it takes an energy that is about 4 times kT. Of course, if T is smaller, this energy will be smaller and vice versa. If you want to refine the calculation and calculate the energy that is necessary to go from 0.99 to 0.01, it will be about 9 kT, okay? These are small energies. If you consider the room temperature, so the room temperature is 300 Kelvin, okay? And you measure the energy in electron volts, 1 kT is about 26 milli-electron volt, okay? So at room temperature, the first result, 4 times kT, is about 100 milli-electron volt. And the second result, 9 kT, is about 200 milli-electron volt. And these are small energies. This is important from a practical standpoint to examine the behavior of the semiconductor. Okay. Remember, the Fermi level is the value of energy in which the Fermi statistics takes the value equal to 1/2. So it goes from almost 1 to almost 0 in a small interval of energies around the Fermi level. Okay. Also remember, the Fermi statistics can be calculated only in the condition of thermodynamic equilibrium. And also the definition of the Fermi level is well posed only in the condition of thermodynamic equilibrium as well as temperature, okay? Now we take the band structure again of the semiconductors. Actually, it is almost 6, so we stop here for the moment, but in the next hour we shall examine some consequences of putting together the band structure of the semiconductor and the Fermi statistics, because when we consider the equilibrium situation of the crystal, the placement of the electrons of the crystal in the energy state, that is the placement of the electrons in the bands, is prescribed by the Fermi statistics. So at this point, we shall understand why, out of the many bands existing in a semiconductor, only 2 of them are actually important, okay? And the answer, as you shall see immediately, is because they are near the Fermi level, okay? They are near the Fermi level. We stop here for a few minutes and we shall resume at 6:10. If there are questions, you can put on the mic and ask questions now. Okay, sorry for the delay. We start now, and I have checked the recording, so nothing has been lost in the recording on the first few minutes. So the mic was off, but the recording was on, and it will be loaded later on. So we resume now. And we introduce for the moment a concept that will be specified better later. You remember we already anticipated that when we consider a system made of many particles, it is impossible to describe individually the dynamics of each particle. So we must use some statistical method that consists in describing the system of particles collectively. We have to introduce the concept of distribution function. The distribution function is a more general concept with respect to the Fermi statistics, because the Fermi statistics applies only in the equilibrium condition, whereas the distribution function applies in any situation. So if we consider a system of fermions that is not in the equilibrium condition, we use the distribution function. If the system of fermions goes to equilibrium, then the distribution function transforms into the Fermi statistics. So the Fermi statistics may be considered as a subcase applicable only in the equilibrium condition of the more general concept of distribution function. We start with an easy example, that is the example of a discrete distribution function. So a distribution function that depends on time and on an integer index. A possible example is, consider a faculty of the university. This faculty has many rooms, and we want to determine the number of students that are inside each room at any instant of time. Okay, so we don't care about which is which or who is who of the students. So we don't want to know the name of the students. We simply want to know how many of them are there. So in this example, F1 at time t indicates the number of students that at time t are inside room number 1. F2 is the same for room number 2, Fs is the same for room number S. Okay? Of course, you may think that each room is a subdomain of the faculty. Okay? Now, of course, the distribution function is not limited between 0 and 1. You may have 10 students or 200 students and so on, okay? So it is not a probability. However, we can express the distribution function in a form that exhibits a probability. For instance, still remaining in the example of the students of a room, okay, you may calculate the number of students in a room by considering the total number of seats that are available in the room, like CS is the number of seats. And then you multiply by phi s, where phi s is the fraction of seats that are occupied. So for instance, if you have a room with 20 seats and the fraction is 1/2, then you have 10 students in the room, okay? It is unlikely that you can find in a room 2 students sitting in the same seat, okay? So in this case, the fraction of occupied states is some quantity that goes between 0 and 1. So you can apply the exclusion principle also to students and consider that phi s is limited between 0 and 1, so you can consider phi s as occupation probability. It is a probability proper. Then you can still elaborate on this. For instance, if CS is the number of seats in the room, you can consider that this number of seats is equal to the product of the density of the seats, that is the number of seats per unit area of the room, times the area of each seat. Okay, it looks very stupid to go so deeply into this calculation, but if you consider that we have already encountered the concept like the density of states, okay? So you can express the number of seats in a room as the product of the density of seats, number of seats per unit area QS, times the area occupied by each seat, okay? What is the total number of students of the faculty at time t? It's F1 plus F2 plus etc. So it is the sum over S of F, and that sum can also be written as sum of the products CS phi S, or if you replace psi S as QS omega S phi S, okay? Now we have to transfer this in the language of the crystal, okay? So first of all, we go from a description using discrete variables to a description using continuous variables. So the area of each seed, omega s, becomes an infinitesimal quantity. And for the moment, we think of it as the elementary volume of the space, okay? Because of this, also CS, that is, you remember, it used to be the number of students, okay? Sorry, the number of seats, okay? Becomes equal an infinitesimal quantity that is the density Q times d omega. And finally, the occupation probability, instead of being function of time and a discrete index S, becomes function of some omega that we shall specify, nt. And similarly, f of s becomes a function of omega nt. So omega for the moment is the space in which we describe the elements of the system. Now we remember that the elements of the system are particles. And particles in the quantum description are described by a position, and the position is R, by a momentum, and this momentum in the quantum case is represented by K, that, as you remember, is proportional to the average momentum. And finally, there is a dependence on the probability, a dependence on time, okay, in general, in a dynamic situation. So now we have the picture in which the distribution function depends on R, K, and T, and the probability of occupation depends on R, K, and T. So what is now the meaning of the distribution function? If you take the distribution function f and multiply it by the differential of R and K, you can see it written on top, d3R times d3K, okay? d3R times d3K is an elementary volume of the combined space made of the R and K coordinates. So the meaning of the distribution function now is that the product of F times d3R, d3K is the number of particles that at time t belongs to that elementary volume d3R, d3K. And similarly, we can find the total number of objects. You remember in the previous page, the total number was found by adding up over the index. Okay, now the index has become R and K. So from discrete to continuous, in order to find the total number of objects, we must integrate the distribution function over R and K. And another possible expression is integrate Q times phi again over R and K. This gives you the total number of particles of the system by definition of the distribution function f. Of course, it is not prescribed the order in which we perform the two integrations. We may start by integrating over R and next integrate over K, or we may decide to integrate over K first and later we integrate over R, okay? So this is shown in the next line. We may perform the integration over K first. So we integrate over K the distribution function f, okay? So the integration over K gives you a function in which there is no dependence on K anymore because we have integrated over K. So this integral depends only on position R and time. If we perform the next integration, so that if we integrate over the physical space R, we obtain the total number. But this means that the integral of f over K only is the concentration in the physical space, because obviously if you integrate the concentration, you obtain the total number. So this is an important aspect to be remembered. The integration of the distribution function over the K space only provides the concentration of the particles in the physical space R. And in general, we do this because we are more interested in the concentration than in the total number, okay? When we consider a crystal, you remember Q in this language is the combined density of states in R and K. So it is a constant that we already know. It is 1/4 pi cube, okay? So in crystals, Q is a well-specified constant. Also, you remember that in crystals, due to periodicity, all the physical information about the functions involved in the analysis are defined inside the Brillouin zone, okay? So the integrals with respect to K must be carried out or extended over the first Brillouin zone, okay? Integrals, if necessary, integrals over the physical space will be extended over the volume of the crystal, okay? We shall have not so many occasions of such an integration, but just to remember. So the integrals over K go over the Brillouin zone. The integrals over R go over the volume of the crystal, okay? So this is a general introduction about the distribution function. We now introduce a more general definition of the density of states. You remember we have been talking about the density of states on Tuesday with reference to a parabolic band. So we introduced the density of states considering a relation between energy and K that was parabolic, because that is the easy case, okay? And you remember that we found that in one dimension it is inversely proportional to the kinetic energy, in 2 dimensions it is a constant, in 3 dimensions it is proportional to the square root of the kinetic energy, okay? However, the density of states is a more general concept because it applies also in situations in which the relation between energy and momentum is more general. It's not necessarily parabolic, okay? So we are now introducing this more general definition, and we assume that we know the relation E of K. We consider a single band, for instance, the conduction band of a crystal, okay? And we consider the form of the branch. E is equal of E of K1, K2, and K3, not necessarily parabolic. And then we introduce two more variables that we call alpha and beta, also depending on K1, K2, and K3. You may think, for instance, of a transformation of variables from the Cartesian coordinates K1, K2, and K3 to the spherical coordinates E, alpha, and beta. So E is like K squared, so it's the radius, and alpha and beta may be two angles, okay? This is just an example. This transformation is completely general, okay? It's just a transformation from a triplet of variables, K1, 2, and 3, into another triplet of variables, energy, alpha, and beta. Then we assume that this transformation is invertible, so that we can also write K1 as a function of energy, alpha, and beta, and the same for K2 and K3. And since we must perform integrations, you remember, when you change the variables in an integration, you have to change also the differential. So you need the Jacobian determinant of the transformation, okay? In general, the Jacobian is indicated with J, with the symbol J, but since very soon we shall consider the current density that is also indicated with symbol J. In this case, I have been using H. So H is the Jacobian determinant of the transformation. So it is symbolically indicated in this form. You remember it is a 3 by 3 determinant whose elements are derivative of K1 with respect to E, with respect to alpha, and with respect to beta. Then the second line is derivative of K2 with respect to E, alpha, and beta, and so on. Okay? Then you calculate the concentration. Remember, the concentration, you see it here, is the integral of F over K alone, and F can be written as Q times phi, and phi is a probability. So the concentration, if you look at the first line of the page, is the integral of Q phi over K. And then you decide to perform the integrations over alpha and beta first. And then you perform the integration over E last. So what you do is that you change the variables from K1, K2, K3 into E, alpha, and beta. So you have d alpha, d beta, dE, and then you have to write down the Jacobian. Phi depends on E, alpha, and beta. It also depends on position and time. They are simply not written in the first line, okay? What are the integration limits of energy? If you consider of a crystal, you remember the energy will start from zero. There will be some zero of energy at some position. And then when you go up, you have infinite bands. So the integration over energy must go from zero to infinity. But in a crystal, you have allowed bands and forbidden bands. You remember, you have an alternation of bands that contain the states for the electrons and forbidden bands with no states. So when you perform the integration over energy, you can do it as is shown in the second line. You split the integration interval of energy into the bands. So the integral over delta E1 is the extension of the lowest band. Then you have a forbidden interval, so you don't care about it. Then you have the integral over the second band, and so on. So you integrate over all bands of the crystal. You remember the whole integral on the left-hand side provides you with the concentration of the electrons of the crystal. So the first integral over delta E1 alone, which is limited over the first band, will give you the concentration of the electrons of band number 1. Call it N1. The concentration of the electrons is indicated with N because the electrons are negative particles, okay? Then you have N2 and so on. So this is easy. It expresses the fact that the concentration of the electrons of the whole crystal is the sum of the individual concentrations of the bands. How does the concentration of one single band look like? It is indicated in the third line. It is the integral over the delta Ej. J is the counter of the band. It could be 1, 2, etc. Okay? Delta Ej is the extension of band number j in energy. And then you have the integral over the other two variables, alpha and beta. Okay? Now, take a special case. Assume that the band that you are considering is completely filled. Every possible state of the band is filled. Okay? That means that the probability of occupation of a state, phi, is equal to 1 for this band that you are considering. Okay? So in the integral, you consider phi equal to 1 for a moment. Okay? And you are left with the integral over delta Ej of the quantity gamma written here. Obviously, gamma is the integral of Q times H over alpha and beta, because phi, by hypothesis, in this band is equal to 1. Okay? Obviously, if you count the total number of electrons in a band that is completely filled, since each electron fills one state, counting the electrons in this case is equivalent to counting the states. but this is an integral only over K, so it gives you the concentration. That means that the integral of gamma over delta Ej is the concentration of the states in space. Okay, so it is the gamma alone is the combined density of states in energy and physical space. So this gamma is the generalization of the gamma that we already encountered for the parabolic case. In that case, because the shape of the band was parabolic, it was easy to calculate, to bring the calculation to the end. So the form of gamma in that case is given. This is a more general definition of gamma, but the concept is the same. Gamma here is the density of states in energy and physical space. Okay. Now, you can take again the double integral on the third line. So if you look at the third line, you have a double integral over alpha and beta. Take that double integral, okay, and divide it by gamma. Gamma is by definition the double integral of QH, okay? So you obtain the ratio of two integrals as shown in the mid part of the page, okay? This ratio is strictly positive because if you look at it, Q is a constant, is a positive constant. You may cancel Q, okay? H is the Jacobian determinant. You remember that you take it in modulus. So H is a strictly positive quantity. And phi that appears in the numerator is a function that is between 0 and 1. So the numerator is strictly positive. The denominator is also strictly positive, but the numerator is smaller or equal than the denominator, because in the numerator we have phi, and phi is smaller, maybe smaller than 1. Okay, so the ratio that is called P depends on energy, because we have saturated alpha and beta in the integration, and then it depends on R and T. So P is a quantity that is always between 0 and 1. So it can be thought of as a probability. And finally, if you multiply both sides of the expression that is defining P, if you multiply both sides by gamma, and then you integrate over the band energy, you obtain again the expression of the third line. So if you compare the expression of the third line of n sub j with the expression that is a little bit lower, near the double arrow, okay, you see that we have found an equivalent expression of the concentration of the electrons. The concentration of the electrons in a band can be obtained by integrating over the energy of the band the combined density of states gamma times the probability of occupancy of the state E, that is indicated with P. P is not the Fermi statistics, because this calculation that we have just finished is much more general. It does not assume any condition of equilibrium. It's completely general, okay? Obviously, When we consider the equilibrium case, then the occupation probability of energy P must become the Fermi statistics. Okay, so at equilibrium, P becomes the Fermi statistics, so time disappears at equilibrium because there is no dependence on time in the equilibrium condition. The dependence on R may be left because if, for instance, the semiconductor is non-uniform in space, we may still have a dependency on R, okay, in the equations, okay? So this calculation looks difficult, but it is just a matter of definitions, is a way to define formally the probability of occupation in energy in general, okay, and provide the expression of the concentration of a single band. We also have the possibility of exploiting this definition to introduce in a more formal way the concept of hole. Okay, we have just indicated the name hole, talking about the bands as missing electrons. Okay, we can do better than that. We can consider again the definition of the population of band number J, the one that is here near the double arrow, okay? And then, after observing that P is in any case limited between 0 and 1, we play a trick. We call P equal to 1 minus P. It's just a mathematical trick. We add and subtract 1, okay? And then after that, we replace this form into the integral. The integral with the 1 gives you this quantity, integral over the band of gamma, okay? And you remember, this is just the total concentration of states, because we are counting the population of electrons as if each state is populated by one electron. So this is equivalent to counting the number of states, okay? So this is the concentration of states. The second integral is the integral of what? Well, we have gamma, that is the density of states, and then we have 1 minus P. On the other hand, P is the probability that the state is filled. So 1 minus P is obviously the probability that the state is empty, okay? So if we consider the density of states times the probability that the states are empty, and then we integrate over energy, we find the concentration of the empty states. The empty states are called holes, and the concentration of the holes is indicated with symbol P. So Pj is the concentration of the holes of band number J. Holes are indicated with P because in the dynamic situation they behave like positive particles. So this is the reason of the P, okay? It is not strictly necessary to define P using gamma, okay? We may also define P using the original symbols, so that is considering the density of states in the phase space and then multiply by 1 minus phi, that is the probability of occupation in the phase space R and K. We can do the same in this form, okay? So this integral of q times 1 minus phi is an integral over k, so it must be carried out over the Brillouin zone, but we consider only the energies of a single band, band number j. This is the reason for the symbol j in parentheses that you can see here. So these two definitions, one using gamma and p and the other one using q and phi, are fully equivalent to each other. What happens if we consider a crystal in the equilibrium condition, and then we combine the structure of the bands and the information about the Fermi statistics? You know that at equilibrium, the probability of occupancy of a band is given by the Fermi statistics. And the Fermi statistics has two parameters in it. One is temperature. It is the temperature of the crystal, in this case. And the other parameter is the Fermi level, okay? So when you have an alternation of allowed bands and forbidden bands, like you have in a crystal, there are only two possibilities for placing the Fermi level. It may happen that the Fermi level is inside an allowed band, or the other possibility is that the Fermi level for that specific crystal happens to be in a forbidden gap. Okay, of course, there is still a third possibility that it is exactly at the boundary between the gap and the band, but this is a limiting case, okay? So there are just two possible cases. Case one, the Fermi level happens to be inside a band. The other case, inside a forbidden gap, okay? This is the first case, what you see in the figure. For those of you that have some copy of the book, there is a misprint. In the book, this gamma here is indicated with G. It is a mistake, so it must be gamma, not G, okay? So how do we interpret this figure? If you start looking from the left, you have two bands that are the gray area, okay? Separated by a forbidden gap of extension EG. One question, you are accustomed to see the bands as curves, okay? As E of K curves. In this case, the representation of the band is assuming that in the vertical direction you have energy, but in the horizontal direction you have space, physical space, X, not K, okay? So the bands are uniform with respect to position. They depend on K, so this is why the figure is different. In the second part of the figure from the left, you have the combined density of states, gamma. Be careful that the diagram is rotated. So here, the energy axis is vertical, and the function gamma is shown on the horizontal axis. So the two axes are inverted, okay? So these two curves in black represent qualitatively the density of states. You remember that in the parabolic band approximation, the density of states behaves like the square root of the kinetic energy. Okay, so this is a square root of E minus a constant. And this is also the square root of a constant minus E when looked at from the vertical axis. Okay. Then we go to the third part from the left. This is obviously the Fermi statistics, again with the two axes inverted. Okay, so when you go up in energy, the function P goes to 0. When you go low in energy, it goes to 1. And when we consider an energy equal to the Fermi level, the function is equal to 1/2. Okay, so this horizontal dashed line is the position of the Fermi level. You see, the Fermi level happens to be inside the upper band. Okay. Why is the Fermi level called EFI? I stands for intrinsic. So this is a crystal with no impurity, pure crystal, intrinsic. Okay. Then you can also see familiar symbols. EC is the dashed line that is the lower edge of the upper band. EV is the other dashed line. It is the upper edge of the lower band. Okay, so when it happens that the Fermi level is inside a band, that band is called conduction band. So rightfully, the lower limit of it is called EC. EC is the lower limit of the conduction band. The band that happens to be just below the conduction band is called the valence band. Okay? So EV is the upper edge of the lower band. Okay? At this point, we may calculate the concentration of the particles in the two bands. It will take 2 minutes. Okay? We simply apply, for the conduction band, we apply this integral. We take the density of states gamma multiplied by P. In this case, P is the Fermi statistics because we are in the equilibrium condition. We integrate over the energy of the band and obtain the concentration of the electrons. Okay? So we multiply qualitatively in the figure gamma times the Fermi statistics. You see, gamma is 0 here. P is almost 1. So the product here is 0. Then the product is this line becomes larger because the density of states becomes larger, but then the Fermi statistics goes to 0 exponentially. So the product also goes to 0 exponentially. When we integrate over energy, we simply obtain the area subtended by this curve. That area is the area of gamma P, is the concentration of the electrons of the conduction band. For the valence band, we calculate the concentration of holes. So we must take gamma times 1 minus P and integrate over energy. But you see immediately that P here is already equal to the limiting value 1 when we enter the valence band. So 1 minus P is 0. 0 times gamma gives you a 0, and the integral is 0. That means we do not have any hole in the valence band in this case. On the other hand, if we don't have any hole, that means that there are no empty states in the valence band. That is, the valence band is completely occupied by electrons. So you remember it cannot contribute to the electric conduction. The conduction band instead can, because the Fermi statistics is smaller than 1. So there are states that are empty because the probability of filling the states is smaller than 1. So the conduction band contributes to conduction. So in this case, which is typical of metals, we have a crystal in which only one band contributes to conduction. We stop here, and then we shall continue tomorrow to complete this discussion. If there are questions, you may put the mic on. Okay, so I don't see any questions, neither by voice. Okay. So thank you, bye-bye. Meet each other tomorrow.